Hello students, in today's lecture I will discuss the differential vector identities which are required to be used in electrostatics and magnetostatics. Differential vector identities which I am going to state and prove relates del operator with scalar function or a vector function or a position vector. The expression for the magnitude of the position vector is given here. Beside this, the expression for the gradient of the scalar function, divergence of the vector function and the curl of the vector function is given in this slide. The first identity here is vector del dot vector r equal to 3. In words, we say that divergence of the position vector is equal to 3. Let us prove this identity. Now for this identity and for other identities, we'll start with left hand side and then we'll simplify it to show that it is equal to right hand side. So let us start with the left hand side, which is equal to vector del dot vector r. Now this is a dot product of the del vector and the position vector. In the dot product, we use the formula as the sum of the product of the component. So the components of the del operator are dou by dou x, dou by dou y and dou by dou z. Component of the position vector are x, y and z. Now let us try to differentiate this partially. So in the first term, dou x by dou x is 1, second term dou y by dou y is 1 and third term dou z by dou z is 1. Therefore, 1 plus 1 plus 1 equal to 3, which is equal to the right hand side. So we have proved the first identity. The second identity is vector del cross vector r equal to 0. In words, it is curl of the position vector equal to 0. So to prove this, let us start with the left hand side, which is del cross r. We used the formula for the cross product, which is evaluated as 3 by 3 determinant. In this 3 by determinant, the first row has a coefficient of unit vectors I cap, j cap, k cap. Second row are the components of the first vector, which is del, whose components are dou by dou x, dou by dou y and dou by dou z. Third row is the component of the second vector, which is here vector r, whose components are x, y and z. To evaluate this 3 by 3 determinant, we convert into 2 by 2 determinant. Now here there are 3 terms containing 2 by 2 determinant. The multiple of that are the coefficient of the first row with the sign alternate. So here it is plus I cap minus j cap plus k cap. To find this determinant whose multiple is I cap, cover the row and column containing I cap and whatever remains here, you write it in the same order. So here these are written as dou by dou y, dou by dou z and y, z. Then to get the coefficient of the 2 by 2 determinant whose multiple is j cap, cover the row and column containing j cap and whatever remains here, write in the same order in the second term inside the 2 by 2 determinant. And its first row is dou by dou x, second and dou by dou z, second row is x and z. Similarly, to find the coefficient of the 2 by 2 determinant whose multiple is k cap, cover the row and column containing k cap, and whatever remains here write in the same order in this 2 by 2 determinant. So coefficient of this 2 by 2 determinant in first row dow by dow x, dow by dow y, and the second row x, y. Next, evaluate this each of these 2 by 2 determinant. To evaluate this 2 by 2 determinant, go from left to right. So find the product of the diagonals, that this into this, and subtract this into this. So when we evaluate this 2 by 2 determinant, in the first term it is dow z by dow y, we write it here, minus dow y by dow z. Similarly, in the second determinant, you multiply the diagonals and subtract from left to right, and we get here dow z by dow x minus dow x by dow z. Similarly, in the third term, dow y by dow x and dow x by dow y. The next here, in this step, we see that dow z by dow y is 0, because here when you differentiate partially with respect to y, x and z is constant, so it is 0. Then this in the first term, the second term, this dow y by dow z, since we are differentiating partially with the z, y is constant, so that is 0. So therefore, each of this quantity will become 0, so it will result into 0, which is right hand side. The third identity which we are going to prove is del of dot product of vector A dot vector R is equal to vector A. In words, it is gradient of the dot product of vector A dot vector R is equal to vector A. Now here, vector A is a constant vector. The constant vector means its components are constant. It does not contain x, y or z. So vector A equal to A1 I cap plus A2 j cap plus A3 k cap, where A1, A2, A3 are constant. So let us start with the left hand side, which is del dot product of vector A dot vector R. So first let us find out what is vector A dot vector R. So we use the formula for a dot product, which is the sum of the product of the components of the two vectors. So here the components of the vector A are A1, A2, A3, vector R are x, y and z. Now sum of the product, that is A1 x plus A2 y plus A3 z. So now this is in fact a scalar function. So we find gradient of this scalar function. So del of this scalar quantity, there is a gradient of the scalar function. We use the formula that dow by dow x of this scalar function I cap plus dow by dow y of this scalar function j cap plus dow by dow z of this scalar function into k cap. Then let us evaluate the first term. This dow by dow x of a1x plus a2y plus a3z I cap. So we will try to differentiate partially with respect to x each of this term in the bracket. So partial derivative with respect to x of a1x, a1 comes as a constant multiple, partial derivative x with respect to x is 1, plus the partial derivative of this a2y with respect to x. Now since a2 is constant and y is also constant, because we are partially differentiating with respect to x, so that is 0. Similarly, the partial derivative of a3z is 0. Then in the second term, partial derivative with respect to y of this term, see the partial derivative with respect to y of a1x is 0, because a1 and x is constant. Partial derivative of a2y with respect to y is, a2 comes as a multiple and derivative of y with respect to y is 1 into that j cap is written here. Partial derivative of a3z with respect to y is 0. Similarly, in the third term, the partial derivative of a1x with respect to z is 0. Partial derivative of a2y with respect to z is 0. Partial derivative of a3z with respect to z is a3 into 1. So, into that vector k becomes a3 vector k. And this is nothing but this constant vector, vector a, which is equal to right hand